Okay, so for our first problems here, we're looking at our graph telling what our limit should be. So in number 1a, the limit as x approaches negative 1 from the left looks like it's going to be 0. And then in part B, the limit as x approaches negative 1 from the right looks like it's going to be 0. And therefore, again, our limit value is 0. For number 2a, the limit as x approaches 0 from the left looks like that's going to be negative 1. 0 from the right looks like that's going to be 3. And so notice the limit from the left does not equal the limit from the right, so this does not exist. Looking at the next part, we have the limit as x approaches 2 from the left. That looks like that's going to be 3. The limit as x approaches 2 from the right, that's going to be 1, and therefore again our limit does not exist because the left and right limits did not match. Our next problem, x approaches negative 2 from the left. So looking at negative 2 from the left, looks like we're going to have 1. From the right, it looks like we're going to have 1. Therefore, that limit is 1. And then for number 5, it looks like the same again. X approaches 4 from the left is going to be 1. From the right is 1. Therefore, the limit itself is 1. In question 6, more of the same, but now we're going to tie in our continuity idea. So for number 6, the limit as x approaches negative 1, that limit was 0. F at 0, we need the actual function's value at 0. Notice that, or at negative 1, and that is going to be 0. But notice in part C, we're asked, well, in part C, is f continuous at negative 1? And we're going to say yes, but we need to explain why. And we do have to do that. Just a simple yes or no is not going to work. Yes, and the reason why is because the limit as x approached negative 1 of our function, that limit existed, and its value was the exact same value of the function at negative 1. All right, so now let's look at number 7. Number 7, again, our limit as x approaches negative 2 here was 1. The actual function's value was 4. So are we continuous at negative 2? And the answer would be no. And again, you have to state why. And we're going to say that the limit as x approached negative 2 of our function does not equal the actual function's value at negative 2. Number 8, very similar. Number 8, notice that our limit did not exist. The actual function's value at 0 is negative 1. And here in part C, are we continuous at x equals 0? And the answer is no. And the reason why here is because our limit did not exist. The limit as x approaches 0 for our function does not exist. So we can't be continuous. Number 9, the limit as x approaches 2, again, we had does not exist. Part B, the actual function's value was 1. And so for C, are we continuous here? And again, that answer is no. And the reason why it would be because the limit as x approaches 2 of our function does not exist. Number 10, our limit value as x approaches 4 was 1. But f at 4, notice there's no value for that, so that one does not exist. So here on part C, are we continuous? The answer is no. And you could put a couple of things here, but pretty straightforward. If f at 4 does not exist, there's no way you can be continuous here. So I'm going to say no, f at 4 does not exist. For these next problems, we have to classify what kind of discontinuity, and yes, you can be asked this on the AP exam, so do pay close attention to the types of discontinuity. And all of this will deal with our limits. So here with number 11, if I look at the limit as x approaches 1 from the right of our function, let's see, what's that going to be? If I plug in a 1 from the right, it looks like we're going to get 0. And then if I do our limit as x approaches 1 from the left of our function, then we're going to get a 3. So notice that from both sides, these are not equaling each other. One's at 0, the other side's at 3. This is going to be what we call a jump discontinuity. And again, we see that because as x is getting closer and closer to 1 from the right, we're at 0. And as x gets closer and closer to 1 from the left, we're at 3. So there's a big break there on our graph. Number 12, notice here what we have going on. We don't have our inequalities, and we can still talk about our limit though. The limit as x approaches 2 of our function h at x. And as we saw earlier, we're always going to use this equation. We can draw this out again. We had an example last time looking at this where we drew it and saw that you always use the equation. And if I do plug in here, I'm going to get 1. And then if I look at h at 2, we saw that this was just a point. H at 2 is -4. So notice here we have what's called a removable discontinuity. And that's going to be because the function is one value, but the limit is something else. So we have a hole in our graph is what's going on here. Looking at our next problem, here we have the limit as x approaches 1 from the right. Again, we're going straight back to those limits of g of x, and that looks like that one's going to be 2. And then we have our limit as x approaches 1 from the left of g of x. And that looks like that one is going to be 1. So notice our one-sided limits are not matching up. This again is a jump discontinuity. And if you can imagine what's going on, that's going to help you see the why behind that. Okay, so now let's look at our next problem. This one's kind of a strange problem. Again, let's go through our limits. So we're going to have the limit as x approaches 2 from the left of f of x. And that's going to be this top inequality coming in from the left is less than 2. If we plug in 2, we're going to get 3. If we look at the limit as x approaches 2 from the right of our function, that means that we are going to be down here, all of these values to the right of 2. And so that's going to give me 5. And then notice this little middle part right here, that's just talking about the actual function's value at 2, which is -1. So again, our one-sided limits do not equal each other, so this would be classified as a jump discontinuity. For problems 15 and 16, we're going to go through the three-part definition of continuity at a particular point. And so our first step, we have to show that the function's even defined at a particular value. So here, we need to show that f at pi does exist, and so that means you're going to be looking for the or equal to part of the inequality. And so that means we're going to substitute in here. So we're going to have e raised to the pi power, and you're going to leave it just like that. Don't convert that to some kind of decimal, times cosine of pi, and cosine of pi is -1. So we're going to get -e raised to the pi. And so we do have this value existing. Now the next part, we need to go through and establish that the limit exists. In order for us to do that, we have to talk about the limit as x approaches pi from the left of our function. And if we look, that's going to be the bottom part. So we're going to have e raised to the pi times tangent of 3 pi over 4. And so we're going to have e raised to the pi power, and then times tangent of 3 pi over 4. 3 pi over 4 is going to be over in that second quadrant, which is going to be a negative 1. So here we have negative e raised to the pi. Now we have to look at our limit as x approaches pi from the right. And notice that's going to be the same function that we plugged into at the very beginning, and that happens quite a bit. So we're going to have again e raised to the pi times cosine of pi, and we see that works out to be negative e raised to the pi. So our third step, again we had 1, here's our second step, it's our limit. The third step is to show that the actual function's value is equal to the limit value. And so here, our third step, we're going to say that the limit as x approaches pi of our function f at x is equal to negative e raised to the pi, which is equal to our f at pi. So those values are all congruent, and so therefore we could do our little therefore there. F of x is continuous at x equals pi. Right, so by the same process, we're going to look over at our next problem and go through those same steps. So here we need to show that we're continuous at x equals negative 3. So our first step, we need to show that g at negative 3 exists. And that's going to be this bottom portion here. That's going to be 5. And so our second step, we need to look at our limit. And notice we don't have our inequalities, so we can go straight to saying the limit as x approaches negative 3 of g of x is going to be equal to, and if we go plug in, notice we're going to get 0 over 0 here. So we've got a problem. There we're going to get 0 over 0. So that tells us we need to do some kind of factoring or some kind of canceling here. So let's look at that top part. We have x squared minus 9, so that's going to be x minus 3 times x plus 3 all over x plus 3. So we're going to cancel those. Now let's come back and look at our limit as x approaches negative 3 of g of x, which is now our reduced version here, and so that's going to give us negative 6. So right away we see in our third part that the limit as x approaches negative 3 of g of x is not equal to g at negative 3. So therefore, g of x is not continuous at x equals negative 3. 17 is a great example of a free response question dealing with this. In 17, notice that we are asked that we need to know what the two limits must equal in order for our function to be continuous at negative 1. So we have to look at what's going on from the left and right at negative 1. Now be careful, you're not going to come down here and use that bottom part. You're going to use these two. And that's because we're looking at negative 1. So we have to see what's going on from the left and right of negative 1. So in other words, if I go to set up our problem, we're going to have the limit as x approaches -1, but this time let's look at it from the right side of f of x. And if we look at it from the right side, we're looking at all the values bigger than -1. So we're going to look at here, the mx plus k. So notice here that all I can do is plug in a -1 for m, and all I'm going to get is a negative m plus k, because k and m are just constant values. Right, so now let's look at from the right or from the left. So we have the limit as x approaches -1 from the left of f of x. And notice what it tells us. If we're coming in from the left, we're on the less than side, and it tells us there that we should have -3. So what two limits must be equal in order for these to be continuous? Well, the limit from the left has to equal the limit from the right. So in other words, -m plus k, that's what we got from the right side, has to be equal to what we got from the left, which is -3. Okay, so now let's look at the next one. What two limits must be equal in order for the function to be continuous at 4? We're going to go through the same process. We have to look at the limit as x approaches 4 from the right side of f of x. And if we're looking at 4 from the right, then we're at the bottom part, which says that's going to be 3. Because again, we need all those values of x bigger than 4. Now let's look at our limit as x approaches 4 from the left of f of x, and that's going to be in the middle portion. And keep in mind, that means we're still plugging in 4 in place of x, so that's going to give us 4m plus k. So what two limits must be equal in order for this function to be continuous? Well, the limit from the right has to equal the limit from the left. In other words, we have 4m plus k has to be equal to 3. Now look at part C. Part C wants us to find the values of m and k so that the function is continuous everywhere. So we need to take our two equations. So again, let's go back and grab those two equations. We had, at the top one, we had -m plus k, and we saw that was equal to -3. And then we have 4m plus k equals +3. So now we have two equations and two unknowns, and you could do any which way you want to solve this system. I would probably multiply this top one by a -1, and when I do that, notice that's going to change to be m minus k equals 3. I'm distributing that -1 to each part, and then I'm just going to bring over that bottom equation, 4m plus k equals 3. And then notice I'm just going to add these equations together like we did in Algebra 1. And if I add m and 4m, that's 5m. Negative k and positive k cancel each other out, which is what I want to happen. That's why I multiplied by the -1. And solving for m, notice we get m is equal to 6/5. Now, we needed to solve for both m and k, so now we've got to go back to one of the two equations, and it really doesn't matter which one. So I'm going to pick on the -m plus k. So that's going to be -6/5 plus k equals -3. And I'm going to add 6/5 over, so I have k equals -3 plus 6/5. And getting your common denominator, that looks like that's going to end up giving you k is going to be negative 9 over 5. So here's your two values. K is negative 9/5 and m is 6/5. Okay, so for these other problems, very similar. We need to find the value of our variables so that we are continuous everywhere. So again, all this really comes down to, when you go through your steps, is the limit from the left has to equal the limit from the right. So the setup of this, you're going to see the limit as x approaches 3 from the left of f of x. And notice I'm going to plug in a 3 for x, so that's going to give me 9k. And then I'm going to plug in the limit as x approaches 3 from the right of f of x. And when I substitute in there, I'm going to get 12 minus 11, isn't it? Yep, 12 minus 11, so that's going to give me 1. And so for our function to be continuous, then our limit from the left has to equal the limit from the right. So therefore, we're going to say 9k equals 1, so k has to be 1/9. So there's our k value. So again, this step here is coming from saying the limit as x approaches 3 from the left of f of x has to be equal to the limit as x approaches 3 from the right of f of x. Number 19, very similar. Same thing again. We've got to look to see where we're going to be continuous. And so we're looking at 1 here. So looking at this, we have to look at the limit as x approaches 1 from the left of g of x. And it looks like if I plug in 1 here, that's just going to give me c. And then the limit as x approaches 1 from the right of g of x. And that's going to be coming down here. So if I plug in a 1 there, I have a negative 1 plus k. And so notice what has to be true here. Our limit from the left has to equal our limit from the right. So that means c has to equal negative 1 plus k. So now we need to figure out, well, what in the world is c or k going to have to be? So if we come down here and look at the limit from the left, limit from the right, we also know that this function here, notice the function's value at 1, g at 1, has to be 4. So we know then that c has got to be 4. That's the actual function's value. So I know c is going to have to be 4. And now we can finish solving for k. And notice k is going to be 5. So I have my two values. Again, c had to be 4. Because again, in order for this to even work, that has to be true. Alright, let's look at our next problem. Again, very similar for number 20. We're showing that we are going to be continuous everywhere. So if we're continuous everywhere, notice we have to talk about both 0 and 1. So starting out with our limit, we're going to have the limit as x approaches 0 from the left of h at x. And the limit from the left is going to be pi. Then we have to look at our limit as x approaches 0 from the right of h at x. And that's going to be this portion down here. And if I plug in 0 there, it looks like I'm going to end up with just b, because all of these x's go to zeros. So right off, I see that here, those two limits have to be equal to each other. So b is going to have to be equal to pi. Now let's move on to the next one. Now we've got to go look from the other direction. And we've got to look at x approaching 1. So here we have the limit as x approaches 1 from the left of h at x. And that's going to be our middle one. And if I plug in 1 there, I'm going to get a plus b. And then I'll look at the limit as x approaches 1 from the right of h at x. And from the right, plugging in 1, that's going to give me 6 plus 5, which is 11. So these two, again, have to be equal. So a plus b has to be equal to 11. Well, to solve for a, I know b is pi, so a plus pi equals 11. So a is 11 minus pi. Okay, number 21. Same idea again. We're going to look at our limit from the left and right. So I have the limit as x approaches 1 from the left of f of x. That's going to be 1 squared or 1. Then I have the limit as x approaches 1 from the right of f of x. And that's going to be sine of x. And so in order for these two things to be continuous, those two limits must equal each other. So we're going to say sine of x equals 1. So I need to know for what x value does that exist for. And sine of x is 1 at pi over 2. So here for sure we're going to get pi over 2. And that x should be a b. Sorry guys, get used to writing x. Okay, so for this problem, they want us to write a piecewise function to represent everything on the right here. And then we have to use the 3-part definition of continuity to analytically justify why g of x is discontinuous at 2 and at 5. And we can look at the graph and tell that, but we have to use some algebra to justify it. So starting off, let's go ahead and try to do our piecewise function, as this would be a good review for us. And so starting out, I'm going to look at just this portion of the graph, and notice that is a parabola, and that parabola is existing from negative infinity up to 2. And so the graph of this, and we're going to try to keep it as simple as possible. I know this is an x squared, and it's upside down, and it's been moved up 5. So what I'm going to do is say that we have negative x squared plus 5, and that's going to be for when x is less than 2. I know it's not equal to because of the open circle. Also, another piece of this, it looks like right here at 2 we have a for sure value of 5. So there's going to be another piece of this. Now that's not a graph, so to speak, it's just an ordered pair. So I know that g of x has a value of 5 when x is 2. Right? So now let's look at our other portion. And on this other side, it looks like we've got this little bitty part here. And so that's just going to be our horizontal line here at negative 3. So I know this value is negative 3 between x values of 2 and what is the other x value? It looks like 5. Okay. And so our last part, and this with the line, there's so many different ways we could represent this line. So looking at it here, it would be good to try to count off our slope if we could, our rise over run. So we would rise up 1, 2, 3 and run over 1, 2, 3. So a good approximation of that would be, it looks like we're going to have a slope of 1. And then if we keep going down, let's see if we can find our y-intercept. So if our slope is 1, that means we can go down 1, back 1, down 1, back 1, down 1, back 1. So that's your x, but we need the y. So down 1, back 1, down 1, back 1. So right there it is. So here it looks like we're going to have x. Our slope was positive 1, so y equals mx plus b. That's what we're doing here. We saw our slope was 1, and we found our y-intercept was negative 2. So this is going to be x minus 2, and that's going to exist for x values that are bigger than or equal to 5. So there's our piecewise function. We've got it all mapped out for us. And now we need to go through and show that we are not continuous at 2 and at 5. So we can go through that with our limits pretty quickly. The first part, you would look at your limit as x approaches 2 from the left of our function. And as x approaches 2 from the left, we get 1. And then let's look at our limit as x approaches 2 from the right of our function. And if we're approaching from the right, we get negative 3. So we can tell we're not continuous here at negative 2 because the limit as x approaches negative 2, or not negative 2, approaches 2 of our function g at x does not exist. And I swapped these. This should be g at x. Okay, and by the same idea, we can show that our limit doesn't exist at 5. So again, same idea here. Go through those steps and you will see the limit from the left doesn't equal the limit from the right, and voila, you are not continuous.